This final set of lectures will be on biaxial loading, and it will be an accumulation of what we've learned so far, in addition to some new information. In this lecture, we're going to view our tower column as a beam column because it experiences both a vertical load from the cables and a moment from the horizontal friction forces. So we'll check for adequacy using a biaxial bending diagram or an interaction diagram. The final project should look like this, where we explore the capacity limits of the beam and then plot our actual load experienced to make sure it's within these limits. So here's a quick shot of the diagram that we'll actually be able to create with our tower section. And we will then plot our load or our demand load on that diagram, and we'll make sure that it's within the envelope that we can say the section is okay. And I'll jump down for a moment to explain this further. So in this case, the x-axis is our moment, which is both the moment caused by the eccentric axial load and the moment caused by horizontal cable forces. So remember, we have a net horizontal force toward the river due to friction over the saddle. That's what we talked about earlier, how we have this force that is creating a moment like a cantilever, and we're analyzing the tower like a cantilevered beam. The y-axis is an axial load from the vertical cable forces. And we will plot the nominal and then factored load capacity for a single tower in order to form the range in which our demand must fall, like I marked with an X here. And remember, the factored capacity is the nominal capacity multiplied by the load factor phi, which if we consult ACI, you may notice drops from 0.9 to 0.6 when our section is tension controlled versus compression controlled. This makes up for the large difference on the compression side of the diagram I've drawn here in green, where it's much less of a difference on the tension side of the diagram down below, which is down here. That I also have drawn in green, but I'll start here for you. Before we dive into these calculations, we need to rule the out-of-plane eccentric axial loading out, so we don't need to use a three-dimensional biaxial loading diagram. And to briefly revisit the eccentricity lecture, we technically have two moments, but the toward-away river moment is what combines with the cable forces and is our main concern. The moment caused by the eccentric axial load that is deemed out of plane or parallel along the river will be ignored because its relative magnitude to the combined in-plane eccentricity and moment due to friction. But if you wanted to, you could check this moment and flip the effective width and effective depth of the beam and check this moment that the beam has adequate reinforcing bar to resist it. Now, a plan view here shows those two eccentric moments, and remember that this should be subtracting from the net moment towards the river, right? Because our in-plane moment is set back away from the center of mass, so because of that offset, we are going to get two moments. One, we'll say here, right, is due to friction, and then due to what I've drawn in red, we'll actually have a opposite moment from the eccentric load. That is going to be acting against it. I'll pop up here for you, where I've drawn this again, showing how they combine. We have our moment pH minus PE and our axial load of P, and they're going to combine as such. Now, in the next lecture, I'm going to start going through how we're going to create this interaction diagram here, and we'll first start by creating the body of the diagram, and then we'll actually define all of the limit points so that we can draw out this nice drawing and be able to plot our demand inside of it.